Okay. So, Pavlo, I'm working for Codecentric, and I have a talk with me which has no slides. Something wrong is happening here. Well, it's okay. So I don't have slides. So it's about a programming language, or at least about a platform. So I go with a demo instead of slides. But before I do this, let's quickly watch a piece of a video of Matrix 2. You know the movie? Does everybody know the movie? Does everybody know what it's all about in the movie? Cool. Yes, I still don't know this, but it's okay. So you watch, do you still hear me? You watch the movie, the music is pretty dramatic, and in order not to lose time, I will speak in parallel. So basically it's a fighting scene from Matrix 2, where one guy is fighting gazillions of clones of Agent Smith. And it's a pretty cool sequence, but it's a little bit brutal, so if somebody is kind of sensible for that, I'm very sorry. The idea here is that we are in the Matrix and we have one guy, Neo, who's actually from the perspective of the machine itself, and the representative of the machine is Agent Smith. He's a problem, he's an issue. So Agent Smith tries to solve this issue by cloning himself many times. And well, we all know how the scene ends, so we will see this by the end. Why do I have this video here? Because this is a good way to explain how actually Erlang OTP works. Did anybody of you ever heard of Erlang OTP? Nobody? Just raise your hands. One guy, and I even know him in person. That's cool. Did you guys hear of functional programming languages as well? You can't hear me? Can you hear me now? I'm very sorry, guys. You should have told me that earlier. So does anybody know Erlang OTP? About Erlang OTP, what is that? No. Functional programming languages? Cool. So Erlang is basically a non-pure functional programming language which has been invented at Ericsson Labs in the middle of '80s, actually for telecom. So they used to get rid of tons of C code and to implement a platform which is well suited for massive parallelism. And this is all about what I will talk about today, this massive parallel approach, as well as the idea of let it crash. This is the main principle behind the Erlang OTP platform. So the idea is pretty simple, but maybe it's a shock for people who are not used to it. So what does let it crash mean? It means that when you have a massively parallel system which has very small pieces running in real parallel and just exchanging messages, when you have a system like that, you cannot predict every single case where things can go wrong. So what you do, instead of trying to catch exceptions and stuff like this, you just let crash these small pieces and try to bring them back and bring the whole system back in a state which is stable and which works. So this is the main idea here. And this is something that is very new for people who are, who see Erlang OTP for the first time. So you see the movie, you see those moves here from Neo. It's actually, it's pretty boring, but it's a cool special effects here. In Erlang, you can have 2 to the 27. Just imagine this number, 2 to the 27 separate parallel so-called actors, or we call them processes in Erlang. They run in parallel. There is a very complex dedicated scheduling which kind of maps to system threads and processes. if it's necessary, because you can even scale further with processes and go beyond this to the 27 border. But anyway, in one single operation system process, you can have this number of parallel actors who are exchanging messages, who are scheduled. So you have it's kind of, it feels very parallel, so it feels very massive parallel, and it tries to utilize the whole CPU time the best way it can. It works internally, it works with event queues and stuff like this, whatever you know from Node.js and systems like this. They didn't invent it, actually. Even Erlang OTP didn't invent this concept, but it strongly uses it. So back to Erlang as language. It's non-pure functional programming language. Basically, the first interpreter was written in Prolog, and it has a Prolog-like syntax. I'll briefly go through the syntax, maybe if I have time by the end of the presentation. If not, we can just sit down outside, whoever likes, and go through some code pieces. I can explain the language a little bit in depth. It's not the point in explaining the language itself here, it's the point in explaining the concept of actually let it crash, of this principle. So here we go, the video is over. So you have seen this sequence. It's pretty stupid. You've seen this sequence, so let's run this sequence in Erlang. Oops. So I will, well, you should read this. Does everybody see it well? Is the size of the font big enough? Great. So actually, I fire up the whole matrix here, and it's an Erlang OTP process, and it starts with Smith creating clones of himself. Of course, Agent Smith is written in Java. Yeah. Yes, well, I mean, programming language communities are kind of biased. I'm used to use the best tool for the best job I can get, and I'm pretty happy to have Erlang OTP in my toolbox now. So just look what is happening here. So actually, it's an attempt. Well, it's not exact down to the second or millisecond with the sequence. It's not totally synchronous with this. But what you see here is when you see this Smith clone number, this number is actually a PID. It's a process ID in Erlang. Erlang kind of simulates an operating system in itself. So it has this notion of process, but we know it from the computer science perspective, we know them as actors. It's just actors that communicate totally asynchronously with each other. They only send messages to each other. And the deal is that the best way you can program in Erlang is to cut your program in very small pieces that are probably runnable parallel. So you kind of satisfy Amdahl's law in the best way you can. And this is the only platform out there which is working like that. So what you see here is PIDs. And when you look at the numbers and when you look at Neo crashing some of them, oh yeah, that's cool. Yeah, now I'm home. No, I'm sorry, it's totally uncomfortable here. So what you see here is, I still need to look at it, but I can show my whole body now. Neo eliminates one after the other. It kind of randomly crashes. Agent Smith instances or clones, but they keep coming back. You see the growing number of them. You will even see more than that. You will even see more than that. Because it's now it's a pretty small number of Agent Smith clones. So back to Erlang. Erlang is it's kind of dynamically typed. We have strong types there. Behind the scenes, the compiler does its best job, its best effort to translate what you code into types and to do stuff like this. But you don't actually declare anything. So you work with variables, but it's not really variables. We're not speaking of variables in Erlang, we're speaking of binding. Like in every good functional programming language, or actually in any good programming language these days, in order to satisfy parallelism or to allow parallelism, you should work with single assignments. So you only once assign a value to a variable, and then it's bound, and you cannot change it anymore. So this is how we code in Erlang. Why is it not purely functional? It's, oh yeah, just wait a second. We have Agent Jackson. Did you see Jackson? You've seen Jackson. Jackson is written in BASIC. Well, his appearance is pretty short, so it doesn't mean a thing. It's just a joke. So just keep on reading. I have some jokes in there. Yeah, so why is it not purely functional? It's not purely functional because the I/O, well, the purely functional language, Haskell, for example, would say you even have I/O as well as something which is also working on single assignment, or it's kind of, well, totally side effect free. We are not side effect free on Erlang when it's about I/O, so you still have to take care of it. But it's a good compromise, it's a good trade-off, because, well, actually it's proved that it works, and it's also used in many systems nowadays, completely outside telecommunication, where it's been invented, or what it's been invented for. It's used, for example, some of the NoSQL data stores like ReaDB or CouchDB are implemented on Erlang, RabbitMQ, and stuff like this. So you can imagine in what direction it goes. So you have massive parallel systems like, well, RabbitMQ. Do you know about RabbitMQ? Yeah, so it has to deal with a lot of parallel messages. So Erlang OTP as a basis for this is absolutely perfect for middleware like that. Or in case of NoSQL data stores like ReaDB in this case, this is pretty impressive because ReaDB is a clone or an implementation of Dynamo paper, however you call it. And it's all about equal nodes that have to coordinate each other. And we shouldn't go deep into the idea of the Dynamo paper and all the abstractions there. But what is important is that Erlang has a built-in distribution. This is another thing. So actually when you pass messages, there is this concept of location transparency. It's kind of a little bit different how you pass messages to processes on other machines. But you can have lots of machines. Empirical value is about 160 in one cluster. They can talk to each other, they exchange heartbeats. There is a basic small protocol behind the scenes. So you run processes everywhere in this setup, and you talk to these processes, exchanging messages, the same way you do in one single process. The principle of let it crash, is something funny happening here? Yeah, Trinity kicks in. Exactly. Don't mistake these jokes here. It's something between men and women here. So again, it has the built-in distribution. And what it also means in terms of this let it crash principle is that in Erlang you have the possibility that one process observes the other process. There are two ways to do this. Either you link them together so they know each other. They can theoretically observe each other. Observing means that when the process A crashes and process B is linked to it, the process B is able, when it sets a special flag, it's able to see this event. It will get a message actually that the counterpart has gone. And this is pretty amazing because it's built in. You can react on this. And you can also do the same in a distributed setup. Well, it's those of you who know better about distributed systems will actually know that failure detection is a very complex stuff, of course, because you can really never know if the process on the other side has gone, or the network in between has gone, or it's just like contention, or it's just too much latency, or if probably it's an animal just bitten into the wire, and the whole network has gone. Are we done here? So you've seen everything, right? Did you see? Yeah. When I start talking, I cannot stop talking. So actually, you see these big numbers, right? I went up to 2001 actors here. And this is absolutely not impressive for Erlang at all. So let me explain what is happening here. I have, when you look at the matrix, let's just scroll it down. When you look at the matrix under this logging started stuff, when the matrix comes up, it's actually an application in terms of Erlang OTP. Erlang OTP has two parts. First, it's a platform with this, well, almost functional language. And it's also a set of behaviors. We call them behaviors. It's abstractions of behaviors that are perfect for massively distributed and parallel systems. So we have abstractions called application, supervisor. Supervisor is a process which observes the other processes, its children, and it can bring them back when they crash, for example. So you define a strategy how it happens, and it's totally declarative. So you don't really have to code anything. Well, of course you have to code something. Sure, you always have to code it, but it's in a declarative way, the strategy, how often they restart themselves and so on and so forth. I will show you the code briefly right now. So what comes up is the matrix itself. There is a neo process. Well, it's main process of neo, it's single one. There is a Smith process. This is the process which coordinates up to 1,000 Smith clones, because we know that there is only one agent Smith. They are not equal. It's one agent Smith, and he starts cloning himself. And we have this unimportant woman and this Jackson written in BASIC. And we also have Trinity, which is actually the reason for the matrix movies to be. But in this particular sequence, her role is pretty small. And you see that I have ever-growing numbers here. So Agent Smith, like in the sequence, starts reproducing himself pretty often. So we go up and go up and go up. They crash, they get brought back. They crash, they get brought back. And I will show you in the code how it's actually done. And we go here up to 1,000 until it doesn't make sense for Neo, so he just disappears there. Okay. Yeah. So back to behaviors before I quickly dig into the code. Application, supervisor, we have workers. Workers are, well, actually, worker is not a behavior. There are different types of workers. Basically, it's servers. So we speak of servers in the Erlang world because it's something that actually has to serve some sorts of requests. Basically, it's something on the network, in the network layer, sockets and so on, or it can be application logic. But you should know that not really many of people take Erlang for real business applications where you have to code business logic. It's for wiring infrastructural stuff. It's real great for that and for middleware like that. Or they take it for gaming, even for implementing chat engines and stuff like this. But it's still, well, it's not the typical business logic you would have in a bank, like, well, I mean, a portal with some logic behind the scenes and with some business objects. It's not for that. So it typically would go with Enterprise Java or something like this. Okay, so worker, the difference between worker and supervisor doesn't do any job. It doesn't do anything except supervising. So its only job is to know about the configuration, how often it has in which situation, and how to restart crashing processes, these workers. And these workers are child processes that even only do a job. They have a job to do, but they don't coordinate. Typically, they don't coordinate. Of course, you can still trick around, but usually they don't coordinate anything. And we have further abstractions, like, of course, in case of when you have network communication, so you have, in a typical protocol, you have steps, right? Like handshake, then let's agree on the basic protocol, let's agree on the next step of the protocol, and so on and so forth. So how would you typically implement this? Better ones would immediately go with a finite state machine, right? So it's like one step after each other, and I switched states. I just go from one step to each state to the other. And there is an abstraction. It's even called finite state machine here. And this is actually something that completely manages the whole matrix here. This is what I will show you. Because even if I have this whole parallelism, I still have to ensure that the sequence is happening. So there are scene changes and stuff like this. Yeah, we have event handlers and stuff. This is not really interesting maybe for this presentation. So let's go into the code. So we start with the application. The application itself is pretty small here. Yes, this is, by the way, Erlang syntax. Don't be scared. Well, you know, languages is a very difficult area. It's like, it's full of tribalism, you know, so everybody is defending his own language, like with the whole heart and soul and so on and so forth. I'm not into judging languages by well, impulsive behavior or whatever. I'm still seeking for the best language I've ever seen. I didn't find it yet, and I tried them, kind of, a lot of them already. Some of them more deeper than the others, because I like them more. Erlang is one of them. Erlang language is pretty simple. It has a small set of what you can do there, but it has real great abstractions for what you know from the functional programming perspective, like list comprehensions and stuff like this. It also has built-in binaries and bit strings, so it's not even necessary that a bit string aligns to 8-bit. It's because of different network protocols, or MP3, for example, you work with like 3 bits and 5 bits and stuff like this. It doesn't align to anything. Well, actually, on the Intel platform, it will align to something, at least to 8. But internally, it's not necessary, so it's prepared for different platforms. So this is Erlang code. Just to briefly explain the syntax, module is just the definition of this module. Dot ends a statement. Minus means preprocessor well, statement. This says that this is an application behavior. It exports explicitly functions. So as I said, Erlang is dynamically typed, so that means that you don't have to declare types. So whenever you have a function which has 3 parameters, you cannot have the same function in the same module which also has 3 parameters and is a different one. So what we have there is a real impressive thing. I'm not sure I have it. Yeah, I have it in the code. I will show this, but I will tell you right now what it is. Ever heard of the concept of pattern matching? Not regular expressions, real pattern matching, where you have function heads, and those function heads are, well, everything is like 3 parameters, right? But you work with arity. This is, by the way, after the slash here in this definition, it's arity. It says export the function start with the arity of 0. That means that there are no parameters or arguments to the function. But anyway, you have the idea that you can describe arguments of the function in the head, like what it should contain. You know? Either a string or a concrete number or a set of a real complex data structures and things like that. So this is the pattern matching. I will show this in different models. So here we go. What is real important is actually this call here. The application starts the main supervisor, and supervisors are organized, typically in a complex application, are organized in trees. So it's a hierarchy of supervisors. Supervisors have child supervisors or direct workers and so on and so forth. And errors can be cascaded, or at least it's a job of the supervisor on some lower level to control its own children, but the supervisor on top will control all underneath and so on and so forth, hierarchically, and it works in a distributed way as well. So you can have supervisors that manage processes on other machines. This is pretty impressive. Okay. What's that? It's Neo versus Smith supervisor, right? This one. So this is the supervisor. The supervisor defines here several child processes. Finite state machine, Neo process, Smith supervisor, Smiths as template, this woman, Jackson, and Trinity. It has a strategy how to restart them. So this is configured here. And that means that when one of them crashes, of the main ones, right? Main ones. So if Neo crashes, for example, the whole application would restart one after the other, one child process after the other here, or the supervisor will actually do this. And it's, as far as I remember, I also always confuse these two parameters. It's either maximum that much in that much time in milliseconds is allowed to crash. Otherwise, the supervisor itself will crash and propagate its crash to the other supervisor, if there is any. In my case, there is no other supervisor. And you define the child as it is here. Well, it's defined as a temporary, so it's when it crashes, it's allowed to come back, and so on and so forth. This is not that important. But let's look into the relevant parts here. Finite state machine. So this is the whole thing that coordinates the whole sequence here. Well, most of the stuff here are callbacks that are dummies. They don't do anything in this application. They should. What I want to emphasize briefly is another feature of Erlang. Erlang has a built-in feature. It's called hot swap. So you can actually exchange code in the running virtual machine. It's not like tricking around with class loaders like you do it on the JVM or JRebel, whatever, however deep you go there. It's not tricking around, it's built in. It was supposed, or an Erlang system was supposed to run forever. You can imagine a machine which is kind of 80 meters under the surface, somewhere in the deep snow, and it has to run forever and forever and forever without a technical staff guy to go there every day, so they can manage it completely remotely. And they can even update the code in running processes, and there are two parallel versions of the same code piece. Depending on how you work with imports, how you use functions here, it's a little bit too much. If you're interested in some more depth in Erlang, I will be able to explain it after the talk in any depth you like. So just take it with you. It has the concept of hot swap, and you can, of course, do this in a distributed manner. That means that you can completely update code on any machine which is visible to you. Okay, this is the finite state machine. And well, what is actually a finite state machine? We know this. So I define a step, a state, and I can define transitions to the next step. So what should happen so I can change to the next step? In my case, it's kind of almost never ending, or at least it steps around with a state called step until there is nothing more to do. And well, this is basically the whole thing here. Here, when the step, let's look in this body here. When I step to the next, when I want to step to the next state, which is again called step, I would just start, for example, a fight sequence, if it's defined like action here, and I would just send to a particular process, I would just send a message, and it will start doing a job, and it will, and then the finite state machine will step further and further and further. Probably what's interesting is to show you how it's configured here, because this is also a tricky part. So here you go. This is how I define the whole sequence here. So the frequency is 5 seconds. Maximum Smiths attacking are 4. Well, it has actually to make sense. And this is the screenplay. This is the way I define here the whole fighting sequence. So what you see here are Erlang data structures. What you have with the curly brace is actually a tuple. A tuple is a tuple. Well, it has elements of any type in it, but we typically start any tuple with an atom. Atom is written in small letters. Well, actually, the first letter has to be small, and it defines the type of the tuple implicitly. So you can pattern match. You can pattern match according to this atom here, and it defines different steps and whose turn is actually is. Smith has to clone himself 3 times, and time giving for that is 3 seconds in the whole sequence. And then step by step, down and down and down and down and down and down. This is how I define it until, yes. So we have the final step is, the final step here is that Agent Smith is looking stupid. Okay. So here we go. This is the FSM, and this is what I wanted to show you. This is actually the pattern matching. I have a step function. The step function has 2 heads and 2 bodies, 2 corresponding bodies. Erlang doesn't have loops, as you know them. I mean, it's a functional language. How do you program loops in functional languages? Can anybody answer this question quickly? Absolutely, yes. So everything is based on recursion. And what we know about recursion, it has to have a base case, right? It has to run down to some case which stops the recursion, or it's endless recursion. Endless recursion will not kill the Erlang process, because only one process will run endless, but you can have 2 to the 27 of them. You don't block a thread or something. It will just not be scheduled. Actually, the virtual machine is savvy enough to know about this situation, and we will completely block out this one. So it will not even give it any computation time anymore. So this is pattern matching, and when you want to do recursion and you want to call functions, and you only have functions, you don't have objects like you know them, encapsulation works through parameters, through arguments, through closures and stuff like this. And pattern matching allows you to define different variations of one function. It's actually what you know from mathematics. When you still remember mathematics from school, or when you're a real mathematician, you know that when you define a function, like with a curly brace, you have different cases for this function, like different branches. And this is the same here in the functional language. You have different branches defined by the head, describing the pattern. And the pattern in this case is, well, anything, underscore means anything, whatever comes. And it has to be this complex data structure with a list and sub-tuples and stuff. And somewhere it has to have this time. When we see this step, we act like this. Or the very final step in my recursion is simply, anything with an empty list. And this is the end. This is where I put the message on screen that you can easily follow me on Twitter. Yeah, it's just a joke. So, okay, this is the supervisor. And let me briefly go into the into the Smith supervisor, because we don't have that much time. Here we go. Smith supervisor is nothing else but supervisor. It has some service functions like clone, for example, to clone a number of Smiths, and it goes into a recursion with an internal function here, which has a base case of 0. This is how we reduce actually a number. So when you have a recursion with a number, not based on the list, when you have a number recursion, you will just probably count it down and have a base case at 0, for example. And then everything has to return a value in Erlang. There is no explicit return statement. So typically we return OK or error, depending on the case, when we don't know actually what to return else, and the calling code needs to deal with that. So it works with, it just dynamically starts children, And it's all those agent Smiths. So this is the whole supervisors that coordinates up to 1,000 of agent Smiths and ensures that there is always 1,000 of them. This is the whole code for that. And let's look at the Neo server. This is actually a worker. And it has a lot of service functions. I mean, the whole code is out on GitHub, so you can check it out and play with it. Or I can show you this afterwards. Just feel free to ask me and to chat with me about this. We have different casts, so it's asynchronous messages, and we have different patterns for them. So when it's a resist message, for example, we do this. When it's a clean message, we do that. When it's a loose poll message, we do this and this and this. So this is the whole scenario. So actually, the finite state machine sends messages to this process, and the process pattern matches the incoming messages out of its message queue. Well, every process has a message queue. We call it a mailbox. You can the process can either pull one message after the other, or it can even do it selectively, leaving all the others in there. And so on and so forth, on and on for different cases. Internally, it's implemented with timers here. How I deal with something has to take 3 seconds or 10 seconds or whatever. Different weapon cases. Yes, and so on. It's a little bit too much for 45 minutes. So, okay. It even sends messages to itself, beating Smith with some logic and so on and so forth. It's not important. The important thing is, probably most of you guys are on the JVM, right? Could you raise your hand who is not on the JVM? 1, 2, okay. So it's .NET? No. Ruby? Oh wow, I'm sorry. No, I'm kidding. You can write pretty cool stuff in Ruby as well. Nice language. So you guys should go for different platforms. Look outside the window. The JVM is perfect for many use cases, but when you have to solve something, we have gazillions. I mean, 2 to the 27. It's like 350 million, as far as I remember the number. Parallel processes, and they feel parallel. They get scheduled. You can even configure the scheduler. It's based on reductions, so it's counting down instructions internally. And when the number of reductions is 0, it gives computation time to the other process, and so on and so forth. And it utilizes the available cores, though it kind of migrates processes from one core to the other through some magic. Well, it's not magic. It's also on GitHub out there. It's written completely in C. Well, actually, Erlang is 80% of C code, and when you write a complex application in Erlang, at some point you will have to write C code. It can work together with Java, but well, it's not the best way to do this. Let's skip it. The message of this whole talk is there are platforms outside that are the best choice for real complex, massive parallel systems or distributed systems. They are perfect for that. They are well proved. People are experienced out there. Community is small because the number of use cases is not comparable to this of Java or .NET, but it's a very friendly community. They answer questions on lists. Even if you dig into the source code, which is also out there on GitHub, Erlang OTP is a complete open source, completely open sourced, and it's even more and more driven by the community, not only Ericsson, or even less Ericsson these days. Look into these platforms. They utilize a very specific programming language here. Some would say the syntax is not perfect. Well, what is perfect? I mean, the Java syntax is also pretty verbose. So nothing is perfect. The language itself is cool, and there are new languages on the Beam. Beam is the virtual machine for Erlang. Like Elixir, it feels kind of Ruby-ish. So Ruby people would love it. really. And it translates actually to beam instructions underneath, and it feels different. So there is a big, there's a growing community within the Erlang community, or even driving new people to the Erlang community through LXC language. Look at that. The concepts are the same. The abstractions are the same. Built-in distribution, built-in let it crash principle, which is amazing when you have to deal with massive parallelism and you really never know what is happening in the system when something crashes. You don't, I used to give a talk on let it crash, a specific talk. You can't even predict anything. You can't even describe every possible situation where something can crash. You just skip it. You just restart processes. Something has crashed. You bring it back up. You give it the same state. The state can still be the reason for the crash. This is a very big problem that you still have to solve. Probably you can step back. But anyway, so look outside. Look at the platform like this. You will learn a lot. If you want to have it on the JVM, there is an experimental project written by Creston Torup and Eric, his co-worker, and I also contributed something as I had more time for that. It's Erlang on the JVM. I mean, it translates beam files, well, the instruction files, the bytecode, the beam bytecode. It translates it into tricky classes on the JVM. It runs newer versions, and they are already working on the Elixir version of it. So feel free to look into it. It's also out on GitHub. It's called Erlang. And you will learn from the language. It helped me two things. First, whenever I use a different language, which is not offering pattern matching, I have to scream, because it's a real powerful feature. It's even powerful when you work with statically typed languages, not even dynamically typed languages. And the second thing, what it has learned me is, for example, I don't reuse variables anymore, even if it's Java. I don't reuse them. I assume it's kind of a single assignment, because what you learn is that this single assignment really helps a lot when it's about massive parallelism, when it's about extreme concurrency, and so on. So this is actually the message, and I hope that well, probably it was too much. If you want, if you like, we can chat outside. I have like 6 hours until I have to give another talk, and I can show you even more code. We can just fire up the Erlang shell and experiment around. I can show you. So probably even if 2 or 3 of you guys are interested in looking into it, learning new concepts for your daily programming, and probably just saying, now I know what I'm missing in Java, for example, it's good enough then. So thank you very much for listening. So now we can answer some questions here. Do you have questions? No questions. Yes, one question.
How would you compare this to Scala and the Akka?
I knew this question actually will come. So when you know Jonas, he's a real big Erlang fan. So actually there is a funny story behind this, but I guess I'm not allowed to tell it in public. But anyway, lot of concepts in Scala, and especially then in Akka, are coming straight from Erlang. Jonas is a very well-known guy and welcomed guy in the Erlang community and Erlang conferences. So he used to speak there actually. And this is when you are totally bound to the JVM, when you have, and I mean, the only operation guys can say no, but we know that they are pretty powerful in enterprises because they can come up with stuff like security and compliances and blah, 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 blah. Boring. But when you're really totally bound to the JVM, and seriously, there are cases where you need to be bound to the JVM, this is the way to go there. Scala, Akka are impressive, but I'm not impressed in that way. I'm impressed how they actually, behind the scenes, how they implement actors, because it's pretty tricky on the JVM. The way Creston does this with Erlang is also pretty tricky. It uses Killim as library, and Killim is also pretty impressive how it does this. So it uses continuation, passing style, simulation, and stuff like this. We can even chat more about this. I don't have time for that right now. But anyway, to answer this question directly, yes, this is the way to go on the JVM. Absolutely. I wouldn't even compare this, because when you look at the source code, how you configure what happens when processes crash, or they call them actors, when they crash, it's the same. It's even almost the same syntax there. Any other question? So go out, check this out from Erlang OTP, this one or the whole Erlang OTP, and feel free to dig into it. You learn the language within, I would say, 1 week. You can write code then. But you will need years to learn the platform itself, like you need years to learn JVM as the platform. It's not that simple like just writing code, right? The language itself is pretty boring. I would never say the syntax is wrong. No syntax is wrong in this world because somebody uses it. But what is real important is the core set of the language is almost nothing. And it's a great fit for what it has to do on this virtual machine here. Okay, so thanks for listening and enjoy your conference, guys.